Okay, cool. It is on Facebook, room?
Yeah.
Is it on YouTube? It's not, right?
No.
What about when you go, because it says that I am.
It's unlisted. You have to go out. The event is unlisted.
It's there? Can you hear me? It's not unlisted.
It's on YouTube.
Oh, no.
It's on YouTube on my computer.
Cool. So can everybody hear me? Says that? Thumbs up? Can you hear me? Okay. Rome, we're good on Facebook?
You're good on Facebook.
You're good.
All right. Well, hello, everybody, and welcome to Gateway to the Cosmos, a live online event hosted by the South Texas Astronomical Society, or STARS for short. My name is Victor de los Santos. I'm the executive director of STARS. And for those of you who have not yet heard of us, STARS is a community-based nonprofit organization. Since the early 1990s, STARS has been providing astronomy and space science outreach to Brownsville and the greater Rio Grande Valley with the help of partners from all over the South Texas area. So joining us for this event tonight are our longtime partners at the Center for Gravitational Wave Astronomy and the Cristina Torres Memorial Observatory. Both of these groups are a part of the University of Texas, Rio Grande Valley, and both of those groups are also based right here in Brownsville, Texas. So tonight is a very special event for us. It's a very special night, not only because it's our first event since March of this year, but because today is also International Astronomy Day and International Observe the Moon Night, which just so happened to fall on the same day here in 2020. So in celebration of these international astronomical holidays, you guys will have the opportunity to, from your homes for the first time, learn directly from Brownsville's scientists about the different types of astrophysics research going on right here in the world's next space city. We're not the first, but we're the next. So the way this is going to go tonight is you're going to hear 4 presentations. The presenters tonight are going to be Dr. Mario Diaz, Wendy Mendoza, Brina Martinez, Richard Camuccio, and Alejandro Reyes. So we're going to get 4 presentations, and then Alejandro Reyes is going to give us a walkthrough of the Cristina Torres Memorial Observatory, where a lot of this research is actually held. During the presentations, feel free to comment on Facebook or on YouTube on the streams and ask us any of your questions that you might have, or you can go ahead and send them directly to us on our social media. We are at Star Society RGV on Facebook, Twitter, and Instagram. So if anybody saw the itinerary for tonight, which mentions all of the presenters I just said, you might have noticed that along with the schedule for the event, we included a solar schedule. So just by joining us here tonight, you'll be able to look out your windows, watch the sun go down, and learn a little bit more about astronomy by actually witnessing it firsthand. So one last thing before we start. If you like what you see tonight, please consider donating to STARS so that we can continue doing more events like this, and so that we can be ready once we're able to meet in person again. If you have anything you would like to donate, you could find the donate button on the Facebook event page, and we will also post it on the YouTube stream. So without any further delays, I'm going to introduce our first presenter, Dr. Mario Diaz. Dr. Diaz is a professor of physics and astronomy at the University of Texas, Rio Grande Valley in Brownsville, and he's the director of the Center for Gravitational Wave Astronomy and the Cristina Torres Memorial Observatory. Dr. Diaz?
Okay. And I'm going to share my screen. And you all can see it, right?
Sorry. Yes, you're good to go.
Okay, good. And well, thank you, Victor, for putting together this amazing event. I think it's important for our community. It's important to get out to the general public about the importance of astronomy and about the things that we get to learn about our universe. So I titled my presentation Sounds of the Cosmos because in some sense, by doing gravitational wave astronomy, is like listening to very incredible cataclysmic events that happen in our universe. Gravitational wave astronomy is related to Einstein's theory of gravity, and Einstein's motivation was varied, but one of the most important things that he achieved when he developed a theory of gravity is to explain a phenomenon that was unexplained for hundreds of years to astronomers of the time. It turns out that Mercury, which is the planet that moves closer to the sun, as it moves around the sun, experiences a rotation, a changing of the position of its orbit around the sun that is called the precession of the perihelion of Mercury. Perihelion means in Greek the point that is closest to the sun. And Newton's theory of gravity couldn't explain this difference, and Einstein's theory of gravity explained it beautifully. It was given the exact amount that couldn't be accounted for in Newton's theory of gravity. And but one of the most interesting predictions, an amazing prediction from Einstein's theory, was something that at the time, Einstein developed his theory of general relativity in 1915. In 1916, he realized that the theory predicted the existence of gravitational waves. What are these gravitational waves? Where you can sort of think about the waves that you see in the ocean. So these are ripples, go up and down, and in the fact of space-time. What is causing this? Well, at the time it wasn't known. Gravitational waves were, to a great extent, a mathematical oddity, and it wasn't clear what were the astrophysical sources. What we knew about the time about astrophysics wasn't all that much, but eventually these waves we knew that had to be originated in the fundamental tenet of Einstein's theory of gravity. So Einstein's theory of gravity doesn't explain gravitation as a force in the same sense that Newton theory does. Newton theory says that the sun is pulling the earth and this force makes it move around. And although the earth also exerts the gravitational pull on the sun, the mass of the sun is so much bigger than the sun wins and makes the earth go around. So for Einstein, there were no such forces. What is the fact that the presence of matter, that energy that is associated with matter, is curving space-time. This curvature that matter originates forces now bodies to move in the geometry that is created by these bodies, like what you see here. So essentially, the sun bends space-time, and this curvature that it generates forces the Earth to move around the sun in orbits that are actually ellipses, but pretty close to being circles. And it turns out, we know and we learned only over the last 50 years or so, that actually the most important source of these gravitational waves are compact bodies. And I'm going to explain what are compact bodies in a minute. They're essentially dead stars that the mass and the small volume they occupy bends space-time. And if you happen to be in a pair, what astronomers call a binary system, this curvature they originate, it keeps moving around just because the two bodies are moving around each other. And these ripples they generate travel. And one of the outcomes, one of the main features that is the result of this bending of a space-time that is changing, producing these ripples, is that the system is losing energy in gravitational waves. And as it loses energy, the bodies are getting closer and closer and eventually crash in producing a gigantic splash of gravitational waves that travel all throughout the universe. So these gravitational waves could have been detected with the LIGO detectors. The LIGO detectors were constructed in the 90s and they operated for now more than 25 years. And there are two of them, one in Hanford in the state of Washington. You see a picture there on your left. And then another one in the state of Louisiana, LIGO Livingston. And the way these detectors work is they have two arms at 90 degrees, about 2.5 miles long each. And they're mirrors, suspended mirrors at each end, and also at the main station that you can see at the corner where the two arms join. And the way these mirrors function is pretty much this. This is a cartoon of the detector, but you can see that a laser, being a very powerful laser, is shot through a beam splitter and bounces back off the suspended mirrors, recombines, and depending on the change in distance of these arms that are changing because of the gravitational waves, the intensity that is collected is changing too, as you're going to see now as these two beams recombine, move to the right on a photodetector. And you can see that essentially the light intensity goes up and down with the change of the distance of the arms, or the length of the arms. And what we see is essentially a change in luminosity and change in laser intensity at this end. And that's the way we can measure gravitational waves. Now, these compact objects, like the ones that I just showed in the previous slide, how do they form? Where do they come from? Well, it turns out that stars shine throughout their life that lasts for many thousands of millions of years through a process that essentially is a nuclear reaction at the core of the star. It's like an atom bomb that is actually more than an atom bomb, like what is called a hydrogen bomb, which essentially is fusing two atoms of hydrogen and making a heavier atom of helium. In the process is burning, generating tremendous energy, and this explosion is balanced by gravity. So the entire life of the star is a compromise between gravity and the thermonuclear reaction at the core of the star. But obviously at some point it runs out of hydrogen because it burns it all, and eventually even helium. And so the star cannot fight against gravity. Gravity wins. Gravity is always attractive, and essentially these bodies collapse. And collapse essentially to three main types of compact objects. Those objects, like our sun, are going to die like a white dwarf. A white dwarf is about a mass typically like our sun or smaller, and concentrated in about the size of the Earth or even smaller. So imagine now something that has 1 million kilometers that is collapsed to about 1,000 kilometers, but still has about that same mass. That's a very compact object. But now with the mass is more than about 1.5 times the mass of the sun. It's even heavier than that. Gravity can win even further, and the star would collapse now to something that's, as I said, that has 1.5 times the mass of the sun, but occupies the volume of a city like Brownsville. It's barely about 10 kilometers in radius. So extremely compact object. Those are called neutron stars. And what happened when the mass of the star is even larger than that? And of course, there are stars that are several times, hundreds of times the mass of the sun, or at least tens of dozens of times the mass of the sun. These stars collapse to form a black hole. Gravity wins so much that essentially everything collapses to a very, very small, tiny volume, and nothing can escape from that volume, not even light. That's the reason why they're black, and we call them black holes. And the first collision of black holes was detected almost exactly, September 14, 5 years ago. And here, what I show is an animation of the black holes are so powerful, so compact, that bend space-time. Then they get together. You can see at the bottom the shape of the waveform, and that we are detecting on the gravitational wave detectors. At 0 seconds, you have the merger of the objects, and then the gravitational waves decay in amplitude, and only a black hole is remnant that results from this merger. And it's something that was probably almost as spectacular. It was an event that happened in 17 August 2017, so 3 years ago. And that gave birth to a new branch of astronomy called multi-message astronomy. And what happened that day is that two binary neutron stars collapsed, and they span the entire electromagnetic spectrum in the associated electromagnetic emission that happened. So the emitted gamma rays, X-rays, ultraviolet, infrared, radio. That means a lot of astronomers, more than 2,000 astronomers all over the world, plus the LIGO detectors observe both gravitational waves, gamma rays, and corroborated in a dramatic manner the prediction of Einstein's about gravitational waves. And the surprises didn't stop there. Just a couple of weeks ago, the LIGO and Virgo collaboration announced an event that happened 17 billion light years away. Two black holes, one about 85 solar masses and the other 66 times the mass of the sun, merged together and formed the heaviest black hole ever detected, that is about 142 solar masses. All the difference in mass here was emitted in gravitational waves, a tremendous amount of energy. And this is called gravitational wave 190521. And the interesting thing about this, nobody was expecting to have black holes with this mass. They were never expected to be black holes in a range that goes between 65 solar masses to about 150 solar masses. And the reason for that lack of expectation is because we know for the explosion of stars that die after the exhaust of their fuel is that if they are within that range of masses, there are certain nuclear processes that are going to make the explosion run away and have essentially the star being ejected, all its matter in space, and nothing is going to be a remnant from that star. At least that's what we thought, that what scientists thought. But then we found stars that are precisely in this unexpected range of masses. And what is the explanation for this? Well, maybe the physics is not exactly what we thought it was. So there's a lot new to learn here from these detections. But essentially, what happens is, and I'm showing now a short movie about this event. And what is interesting is to understand that the way we corroborate Einstein theories, we make numerical simulations with computers. You can see at the bottom of the movie the shape of the gravitational wave as predicted by theory. And what is interesting is that this gravitational wave that is increasing in amplitude and in frequency is making what it's called a chirp, and similar to the chirp of birds. And that's one of the reasons also why we talk about the sounds of the cosmos. But the detectors observe precisely these predicted shapes. And that's the way we can infer the distance to the event and the masses that are involved. But all this listening to this symphony of the cosmos has really just started. There's so much more that we're going to be learning about the evolution of stars. And not only that, eventually with the increasing sensitivity of the detectors, we're going to learn about the origin of the universe itself, because we're going to have enough sensitivity to listen to the gravitational waves that are emitted at the time of the big explosion that started our universe. So the sounds of the cosmos, we are just barely start to listen to them. Thank you.
Thank you, Dr. Diaz. That was an awesome talk. All right, so we have a few minutes now for some questions. So I'm going to start off asking some, and if anybody who is watching on Facebook or on YouTube has any other questions, please feel free to send them to us. We are watching the live chats and we will answer your questions. Dr. Diaz, the first question we have is, what do you see as the next multi-messenger astronomy milestone?
Well, the next multi-messenger astronomy
let me rephrase the question.
That's an excellent, but it's an excellent question. Who's asking that, if I may know?
That was actually Richard asking, so it's another from astronomer to astronomer.
Okay. I think it's going to be difficult, but this is what I like to see. The supernova, the core collapse, a core collapse starts, so it's like a supernova. The supernova is supposed to emit gravitational waves. We don't have a clear theory about the shape of these waves. But if we were we know how to detect it. We've been detecting them for a long time. They're very rare per galaxy. That means the last supernova exploded in our galaxy, it's several 100 years ago. And so the hope of detecting one this century is not all that it might happen. It might still happen. And that would be amazing if we get to observe a supernova and understand exactly how stars die at the end of their lives.
Awesome. So I had a couple other questions, but one thing I forgot that we actually wanted to do is we wanted to ask all of you tonight, what was the thing that first got you, what inspired you to get into the field that you're working in now? What inspired you to get into cosmology and astrophysics?
So now this is a question for me.
Yes.
Okay. Well, I came late in my life into physics. I decided to study when I finished high school when I was 30 years old, and the reason why I wanted to back to high school finish it is I want to understand Einstein theory of general relativity. So essentially that was my main motivation. By the time I finished my PhD and came to the United States and I started working at the University of Texas, LIGO was being built, and I had collaborators, former students, and colleagues that were working at LIGO, and I thought, well, this is probably the best project that I can get involved myself and involve my students as we work on developing a program at the University of Texas. And so my main motivation to come into physics was to understand Einstein theory of general relativity.
Okay. Yeah, sorry, I should have asked you that question first before getting into the presentation questions, but thank you.
Okay.
So, did UTRGV play a role in would you say that you guys played a role in the discovery of black holes in a way?
Well, we form a group of researchers, faculty, and students involved in the detection of gravitational waves, what is called the LIGO scientific collaboration. LIGO stands for Laser Interferometer Gravitational Wave Observatory. And so when LIGO was being built, they attracted many scientists that want to participate in the endeavor of detecting gravitational waves for the first time. And a scientific collaboration was created. We became members of this collaboration. I believe it was formed in 1996, 1995. We became members in 1998 with Professor Joe Romano, who came to work at what was UT Brownsville at that time. And then we started growing our group and collaborating in different aspects of instrumentation, data analysis, and developing also interest myself in the optical follow-up of gravitational waves. That's the reason why I sort of morphed into an optical astronomer and building a project to follow up gravitational waves that is called TOROS.
Okay, thank you. I think we have time for one more question. So we did get one sent to us. That was on Facebook?
Yeah, it was on YouTube.
Okay, so we got from Jose Martin on YouTube. He says, you talked about acceptable ranges for the formation of black holes. Do those ranges apply for whatever happens after two black holes collide?
That's an excellent question. By the way, Jose Martin was the provost of UTV at that time, so he should share some of the success that the group had, because he was extremely supportive as provost of the University of Texas Brownsville of this project. And it's an excellent question, Dr. Martin. The problem is it takes some time. If you get mergers of black holes, then the ending black hole is going to be larger in mass. If you wait long enough, then you, through mergers, you can get binary black holes that are large enough in mass that you essentially cover all the possible range of masses. But the problem is this detection that happened with GW 190521 happened at a tremendous distance, and that means so back in time that from the theories that we have about star evolution, it wasn't possible to have so many encounters between black holes to form those heavier black holes. So in other words, this merger is supposed to have happened from first generation black holes. Those weren't coming from mergers, but from the collapse of stars. At least that's what we think. But of course, the discovery of this event makes a lot of scientists to go back to the drawing board and start looking at the theories again.
Okay, great. Thank you. So we did get one more question on YouTube, and we're running out of time, but this is a really good question, so I really want to ask it. The question is from David Evans on YouTube, and he said, I thought the universe was around 14 billion years old. How could the collision be 17 billion light years away?
It's an excellent question, and let me go back to the slide. There's a mistake there. Thank you for checking that out. It's 1.7 billion light years away. 1.7. It's not quite 2 billion light years away. So kudos to the listener that picked that mistake there. 1.7 billion light years away.
Okay.
Sorry about that.
I was hoping to hear something about how it was so massive that it bent time and the realm of physics.
Yeah.
But okay.
Yeah.
All right.
Yeah.
Well, thank you so much, Dr. Diaz. Thank you.
You're welcome. You're welcome. I'm gonna disconnect now, okay?
Okay.
And stop sharing and stop my video.
And I will start mine. All right. So thank you again, Dr. Diaz. We're going to keep this moving with our next presenter. Our next presenter is Wendy Mendoza. Wendy has a Bachelor of Science in Physics from the University of Texas, Rio Grande Valley. She is currently getting her master's in physics at the University of Texas, Rio Grande Valley. She is the assistant director of the Cristina Torres Memorial Observatory, and Wendy actually specializes in the intersections of astrophysics with different fields of study, such as chemistry and geology, and so you'll learn a little bit more about that on this presentation.
Hi.
Hello.
Happy Astronomy Day. So exciting. Okay, let me just share my screen.
That is Wendy's dog, Bowie. He's getting his degree in, not just kidding.
Okay, so I am in the Survey of Other Worlds, which usually I specialize detecting and tracking asteroids. So this kind of is a little bit of the outline. One of them is what are asteroids, detecting and tracking asteroids, why it matters, which is what's the whole purpose of doing this. So asteroids are small rocky bodies that orbits the sun. They are known as planetoids or minor planets. They are made of rock, metal, and other elements. Usually they are leftover pieces from the formation of the solar system, which is like the formation of Mars, the formation of Jupiter or Earth, and so on. So most of these asteroids are located at the main orbit belt, which is between Jupiter and Mars. And then there are other locations. The Trojan asteroids are usually outside of the main orbit, which is in between the Trojan asteroids. And then we have the Amor object, which is lays on the orbits of Mars. And then the other one is the Apollo asteroids. So these are the near-Earth asteroids that we are trying to detect the most here at the observatory. Usually there are the near-Earth asteroids that could hit us, possibly hit Earth in the future. So there are three types of asteroids. The main three types are the M type, C group, and the S type. So the C types are asteroids that are most common, primarily made of clay, silica rocks, and appear black through grayish. And then the S-type asteroids are greenish to reddish color. They are composed of silicate and nickel iron material. And then we have the M-type, which are the least studied asteroids in our solar system. Many asteroids in this class are made of nickel iron, either pure or mixed with small amount of stones. But these asteroids are it's like a variation of how we have here on Earth. Like we have different types of rock on Earth. So in outer space, we do have different types of rocks with asteroid rocks. So how do we detect them? So we do detect them at the Cristina Torres Memorial Observatory at the Resaca de la Palma State Park here in Brownsville, Texas. And we do have a 17-inch plane wave telescope. This is this one right here, pretty nice and neat. I detected over 50 asteroids, probably a little bit more than that, but that today when I was doing this presentation. And one of the main websites that I use is the Minor Center Planet. So the Minor Center Planet is usually, it's when you can request data from other observatories if you're looking for any astro-specific, or if you want to look at a location where it's going to be located in the next few days. And as well as we put our data there for other observatories, so or other scientists, they can look at our data that we observe. And one of the softwares we use, it's the plane wave. So the plane wave is an interface that controls the telescope. So this, we can put the time, the date, and where the telescope is going to be located. And then, of course, we have the Max DLS, which is the software that we take pictures, our images. And you will know throughout this event how to use those and how do we use those. So one of the near-Earth asteroids that I detected was the 2016 NL. It's classified as a near-Earth asteroids. This was detected in July 9 and 10, 2020. The distance from Earth is 8,469,629 kilometers. Velocity is at 18.1 kilometers per second. And this next close approach will be in July until 2017. As you can see, this is the first image. It's just like a visual presentation how close it is from Earth. So this is the asteroid 2016 LS. Behind it, it's Earth. So it's very super close to Earth. Right here, it's the comparison of the magnitude towards the Julian state. So Julian state is the time, the dates that we detected. It's its magnitude. It's usually it gives us like a light curve, which is a visual presentation how close it is. So if this is higher, if this is higher, that means that it's not that close. If this is lower, since this is the lowest it got, 15.50, this magnitude, it's like the highest one. And I hope you guys can see this, but this is the asteroid that I detected. It's being moved by different images. I want to say I took over 400 images. So yes, so Wendy, what's the whole purpose of doing this? Like, why do we detect this? Of course, asteroids, they can be dangerous. Like the dinosaurs died, they disappear because of an asteroid. Will it ever hit Earth again? It could be possible. I'm not saying it will, maybe, but who knows? And what will happen if it hurt? Well, it's going to be a catastrophe. It will not be great. And can we stop an asteroid? That's my next topic that I'm going to talk about. So there are different asteroid missions. Scientists have planned by blowing up asteroid with a nuke. So they are creating this hypervelocity asteroid meditation mission for emergency response, well known as HAMMER. So they're not trying literally to destroy this asteroid. They are trying to get it separated away from the Earth atmosphere. So they are trying to pull this asteroid closer to the sun. One of the other missions are Russian scientists. They are planning to create this laser, and they are already creating this miniature asteroids in the lab, and they are trying to destroy them by this laser they are using. And of course, the main telescopes that other observatories are doing is the Catalina Sky Survey, the Pan-STARRS telescopes, and the Neowise telescopes, space telescopes that are mostly detecting these near-Earth asteroids, and as well as here at the Cristina Memorial Observatory. Thank you. That's all I have.
Thank you so much for that. Okay, cool. So we're gonna ask a few questions now. We have about 10 minutes for that. And again, if anybody has any questions to leave while you're watching this live stream, please do that on the Facebook chat or on the YouTube chat, wherever you're watching. So the first question that we asked Dr. Diaz and that we're asking you and your cat, if she has an answer, is what inspired you to get into what you are doing right now?
So it's a long story. I wasn't really sure what I wanted to do. It's a very long story. So my main goal is to become an astronaut. I want to do that, and I wasn't really sure what type of astronaut I wanted to be, what I wanted to study, but it all started when I was doing migrant work, and a lot of people were talking about this migrant worker, Jose Hernandez, which is really well known in the migrant community because he was like the first person to get out of that migrant life and actually become an astronaut. So I was like, oh, okay, I want to do that. I wanted to do that, and then I guess during my senior year in high school, I decided to join physics because physics is more related to a study of everything. So that's why I got into physics. And then I really love geology. Geology is one of my favorite things ever, and I wanted to combine it somehow with physics. So one of the closest thing was doing asteroids detection and the importance of asteroid detection as well. So yeah, that's why.
Cool. Amy, oh, I am muted, sorry. Amy Rico asked, what are your favorite types of asteroids? Or what is your favorite type?
I don't have any favorite type of asteroids. I guess the near Earth asteroids, I don't want to say that it's my favorite type because something could happen to us, but they are fun to detect. Any other questions?
Yes. Tito, who actually, my friend Tito, he has been helping out with stars, and so shout out to Tito. He helped actually promote this event, and he's going to be helping out a lot more with stars, and so we're really thankful for him. So sorry, I just had to plug him in there real quick. But Tito asked, are there any interesting resources and elements that could be found on asteroids?
Oh, interesting resources element they could found in asteroids. They are interesting resources elements. I know that the Japanese are kind of taking pieces of those asteroids to test them, as well as they're kind of finding like type of gold inside the asteroid. I have no idea how they're doing that, but that's all I know with their elements. I'm not really specific of other elements that I know.
So I had a question. Actually, sorry, I had some questions, but I'll let other people ask their questions. Eros Rangel asked, are asteroids found by chance, or is there a method of searching for them?
They are found by chance. Like I mentioned, the minor center planet, there are different type of observatories detecting them. There are a method to search them. I haven't not tried them, but I'm gonna do this maybe someday in the future. Since most of these asteroid belts are located between Jupiter and Mars, probably what I'm gonna do is point the telescope towards Jupiter and Mars. Between them, maybe I can find or discover any Earth asteroid for myself. But yeah.
That's so cool. Amy Rico, second question. Well, actually her first question, but I asked her second one first. Would you like to visit Mars?
No. Yes. Okay. I have it. Okay. Mars protect from Earth. So Mars usually protect those asteroids from Earth. I wouldn't really visit it. I will just like stop by and I don't know, grab a cup of tea or something. But I wouldn't just live there.
That's an 8-month journey for a cup of tea. I better be a really good cup of tea. So Amy Rico also asked, she has a lot of questions. What are the requirements to become an astronaut? Do you need a certain degree in science?
You do need a certain degree in the STEM science, which is chemistry, biology, physics, or engineer. How to become one? Well, it's hard. According to their website, you need a bachelor's degree, but that's not true. You need like a PhD to become one.
So I had a question. So you mentioned Minor Center Planet, the website where you actually look for the asteroid information. Is this something that only professional scientists can use, or can anybody look it up?
Anybody is able to access that website. Mm-hmm.
Awesome. We have one more question, I think. I had it somewhere. Sorry, Carol asked, what would you recommend to other teens becoming scientists?
What I recommend? That's a hard question to answer.
Get used to not sleeping very often.
Yeah, it's becoming an astronomer. It's a lot of you don't really sleep that much, but it's a fun process. I really don't know. Depending on the person, how they want to become. Yeah.
So what's your favorite part of it?
My favorite part? I enjoy the nights of observing, and it makes me feel like serving this purpose to protect Earth and doing those type of asteroids. So
That's awesome. Yeah, hopefully we don't become like the dinosaurs.
yes.
All right. Well, thank you so much, Wendy.
Well, one thing I want to mention, there is a near Earth asteroid today. So right now, today, it's near as it could pass. So might have to detect it.
So what are the
Right.
chances that Earth will be hit by a near Earth asteroid anytime
I don't know.
soon?
Anything could happen. Anything could happen. They say, scientists say that it's like a 1% chance, which I don't believe it, because back in 2016, I mean, it hit Russia. And that was like discovered right in that same day that it hit Russia. So who knows?
So
I don't know.
So asteroids could hit and not kill all of humanity, right? Some are more
Depending on the
dangerous
size.
than others, is what I'm saying. Some wipe
Yeah.
out all species, and some are not that bad.
Yeah.
Is that what you're saying?
Depending. Yeah.
Well, all right. Well, thank you so much.
Thank you. Bye.
Bye. All right. So now we're going to move on to our next presenter. Our next presenter is Brina Martinez. Brina is currently getting her Bachelor's of Science in Physics at UTRGV. She is a LIGO fellow, LIGO being the Laser Interferometer Gravitational Wave Observatory that Dr. Diaz told us a little bit about. She is there as part of the Caltech SURF program. So that's the Summer Undergraduate Research Fellowships program. And so she's been doing that for quite some time now. I think it's been 2 or 3 summers that she's been going. And so she's getting really well acquainted with LIGO, which if you remember what Dr. Diaz was saying about it, it's a really cool, really huge machine that uses lasers to detect black holes and neutron star mergers. So yeah, Brina has a really interesting talk about black holes, and she's gonna present that right now. So here's Brina.
Hello, let me share my slide.
Let me unpin myself. There you go.
Okay, so hello everybody. I hope you all are enjoying the presentation so far. My name is Brina, and I'll be talking about listening to the origins of black holes. So when we look at the universe around us, normally we use our eyes. So it makes sense to use instruments like telescopes to help us reach further into the dark sky. And a few different types of telescopes exist, such as optical, radio, and infrared. And these telescopes help us produce beautiful images, like Wendy showed, and other data of the universe, but they all have one problem in common. So only around 95% of the universe will never send us light, and that is a big problem in the search for black holes. So in the universe, there are billions of stars all clustered together in each galaxy, and at far distances, a lot of them look like a single merged spot. And if we try to find a black hole the size of Brownsville within these stars, it is impossible. So how can we solve this problem? We can do it by listening to the universe around us instead of looking. And we have the advantage that black holes make a lot of noise when crashing into one another, allowing the universe to be humming with activity in the form of gravitational waves that Dr. Diaz mentioned, where these objects bend space and time and give us exciting new information in the form of noise, sort of like a clang of a cosmic bell. So I'd like to quickly review black holes so we can understand the complexity of hearing them and knowing their existence by explaining what exactly a black hole is. So black holes, again, were first predicted in Einstein's theory of general relativity in 1916, where he predicts that a sufficiently compact mass object can deform space-time to form a black hole. So these black holes are extremely compact to the point where they are massive enough to bend space-time itself. And to the right, we can see a diagram of what a black hole at the center of a black hole would look like. So at the center, we have a singularity that is infinitely dense, and around it, we have an event horizon, which is the radius around the singularity where matter itself cannot escape due to the intense gravity. And then the photon sphere is what causes the bright ring around a black hole near the accretion disk. And lastly, the relativistic jet that shoots out radiation at the speed of light. And below that image, we can see an actual image of the supermassive black hole at the center of the galaxy M87 from the Event Horizon Telescope. So there are a few types of known and predicted black holes. We have stellar mass black holes, supermassive black holes, primordial black holes, and intermediate mass black holes. So stellar black holes, as we mentioned before, as a star reaches the end of its life, it may inflate and lose mass, and then cool down to form white dwarfs. But larger stars, those around 10 to 20 times the mass of the sun, will collapse and go out with a bang in a massive explosion, such as a supernova, becoming either super dense neutron star or a stellar mass black hole. And these black holes are the most common and can range from a few to about 10 solar masses, give or take. So next up, we have supermassive black holes. These were the ones predicted by Einstein's general theory of relativity, and these can range in masses from millions up to billions of suns. So they are extremely huge, and they are commonly found to have the same size and diameter. So though they can have the same size, their mass can range extremely. And these giants are most found at the centers of most galaxies. So we have our very own black hole at the center of our galaxy, known as Sagittarius A. And these supermassive black holes don't have a clear solution as to how they are formed, but there are a few predictions. Next up, we have primordial black holes. So primordial black holes are believed to be one of the smallest types of black holes theorized. And they are believed to have formed soon after the universe was formed with the Big Bang, where high densities and diverse conditions could have led dense regions to undergo gravitational collapse and form black holes, though no actual evidence is found yet, I think. And finally, we have intermediate mass black holes. So we know small and extremely large black holes can exist, so why shouldn't medium black holes exist? We have the idea that intermediate mass black holes range from 100 to 1,000 solar masses and are predicted to form when stars in a cluster either collide in a chain reaction. And we also know that no individual star collapse could form this type of black hole because of something called pairing instability, which I'll explain a bit later. And then several of these types of black holes forming in the same region could eventually fall together in the center of a galaxy and create a supermassive black hole. So that's one of the theories. Some black holes can create other black holes. So now that we have a bit more understanding of black holes, we can get to how we can listen to them. So quite ironically, I mentioned earlier that the reason we could not see black holes was because of the lack of light in our universe and too much light from stars clustered together. But the way we hear black holes is by using light. And that is exactly what LIGO does. So LIGO, again, stands for the Laser Interferometer Gravitational Wave Observatory, which there are 2 sites currently in the United States, and they collaborate along with other interferometers in Virgo, Italy, and soon Kagra in Japan. And these interferometer detectors use lasers to find the slightest shifts in their journey between 2 mirrors created by colliding black holes billions of light years away. And those are what they look like. They're shaped like an L. So an example of what LIGO has found, we can look at GW 190521, which was the latest discovery released of a black hole merger. So this detection resulted in evidence of an intermediate mass black hole. So that is the first evidence we have of these. So this gravitational wave event is the largest binary black hole merger to date, detected by LIGO and Virgo, resulting in a 142 solar mass black hole and ranges to around 1.7 billion light years away from Earth in luminosity distance, which takes into account the expansion of the universe since the wave was emitted. So this event took around 7 billion light years to reach us. And the 2 component black holes, which were the black holes that formed this larger black hole, ranged at 66 and 85 solar masses, resulting in around 8 times the mass of the sun to be radiated away in gravitational waves. So from the sounds of the collision of these 2 black holes, LIGO was able to provide the first clear evidence of how an intermediate mass black hole was formed. So just to dive more into this detection, it is really unique. And the interesting part of it is one of the component black holes, so particularly the 85 solar mass black hole, there are no clear ways as to how this black hole was formed. So it lies in the para-instability mass gap. What this is, basically, para-instability prevents a massive star to produce an 85 solar mass black hole in this gap between 65 and 130 solar masses. So in para-instability, photons within the star turn into electrons and anti-electrons or positron pairs. And these pairs are not good at holding the collapse of the star, and the star gets very unstable and explodes very violently, without leaving a black hole. So we predict this black hole could be a second generation black hole. So how did this unique black hole form? We know the current black hole formations do not work for this case because of pairing instability. So there are two theories that were created. Theory one was this black hole formed by a merger of previous black holes. So for this multiple merger scenario to occur, they would need to form in a special environment such as clusters of galaxies or AGNs. And if we consider an AGN disk, gas torques from the disk would favor black hole pairing. But for multiple mergers of black holes in dense star clusters, we would expect the black hole to form in a hierarchical merger, such as another event that was seen by LIGO GW 170729, which had the final black hole in the pairing instability gap. And then the second theory is a bit of a dynamical scenario. So this would be where the merger of a massive star with a helium core would merge with a massive star still in the main sequence. This type of merger would lead to a very massive star with a helium core that is undersized with respect to the envelope. And if the core remains within the threshold of pairing instability during the time of a stellar collapse, we can have a formation of a black hole in this gap. And in the dense star cluster, the black hole would find companions dynamically and produce binary black hole mergers with the 85 mass in the gap. So there are a few wild theories of that. And then what we can learn from the sounds of black holes. So the other sounds of cosmos can tell us many things we have yet to discover, but with the sounds of colliding black holes, we now know more than before. Such as proof of the existence of different types of black holes, how often they collide, and we can find the masses of the original and new black holes and new theories to how they were formed. And that is all I have. Thank you. Are there any questions?
Yes, there are. So let's, awesome presentation. Thank you. Black holes are so interesting. So we'll start this off asking what inspired you to get into, black holes, but physics in general and just everything that you're doing now.
Yeah, it's probably one of my favorite questions to answer. So I chose to study physics shortly after taking my physics course my junior year in high school. Before that, I wasn't exposed to physics or astronomy at all, so it was very new to me. But my teacher at the time was a woman who studied physics and worked at NASA before becoming a teacher. And being able to look up to her was wonderful. And I instantly fell in love with physics around the time we learned the topics of black holes and other mysterious objects in the universe. They are honestly my favorite thing to learn about. And I remember rushing back home, opening my laptop and searching every bit of information I could to bring to class the next day and ask. And I still do that today. But mostly I enjoyed the never-ending challenges physics offered. And I was really good at math, so the fact that I got to use math, especially beautiful equations within physics to explain why and how things work, opened a new perspective to me. And with physics, there's always a question to be predicted, answered, or disproved, and someone needs to do it, so why can't that be me?
Yeah, so then something else that, you're right, black holes are really interesting. And when I first found out about them, it's a crazy topic. So something that everybody's wondering and doesn't know too much about them. What happens when you get near a black hole, or if you were to fall into one?
So I wouldn't recommend going near a black hole, first of all, if you ever have the chance, unless you are really curious. But if you did fall into a black hole, you would accelerate to the event horizon I mentioned before, and you would actually stretch and contort. And if someone far away, let's say from Earth, would actually watch you, you'd be moving extremely slow or not at all to their how they see you. And you can try to make a sound, but you're in space, so I doubt that will work. But if you were to flash a light at them, the light would redshift and possibly wouldn't reach them by the time they could rescue you. So when you reach the event horizon, you would actually look completely frozen and stretched. And as the heat engulfs you, you would reduce to ash before you make it to the black hole darkness itself. So, yeah.
It's not a fun way to go. So, so as we all know, space is a vacuum, right? But you're mentioning that this listening to black holes. So how does that happen? How does sound travel through the universe when the space is a vacuum and shouldn't have sound?
Right. So how LIGO works is it uses the lasers to find the shifts from these gravitational waves, and those lasers end up going into a photodiode. And what that photodiode does, it actually converts the electrical signal into an audio, how an electrical guitar turns sound to be heard by humans. And luckily enough, these gravitational waves that LIGO detects are within the human hearing range, so that is why we can hear them. So if they weren't, we wouldn't be able to hear them.
So what you're saying is LIGO is basically a 4-kilometer long guitar string.
Yeah.
That's really cool. I actually
laser guitar string.
Laser guitar string. That is black holes and laser guitar strings. That's it. If anybody needs inspiration to get into this field, yeah, that's it. So how often does so Tito had a question on YouTube. Is there any technology being built or designed to recover high quality audio from black holes?
I'm not sure about recovering like the quality of the black holes. I know there are new detectors coming out or being invented at least to detect different types of black holes or black hole merger events or other merger events that happen in the solar system. So maybe they will have better systems of retrieving the noise that comes from them, but I don't know the specific details of that.
Yeah, because they're building different versions of LIGO, right?
Yeah, there's going to be a space-based one called Lisa, and then right now Cagra that just joined is an underground detector, so that's new. And then there's also another one called Einstein Telescope that's being worked on. So hopefully those make something really cool.
That's so cool, yeah. Like Dr. Diaz mentioned, it worked, right? So Einstein theorized this about 100 years ago, and then in 2015, LIGO found it. And so since then, I'm sure funding and just interest in gravitational waves has just been going off the charts. And now they're building one underground and one in space. So that's awesome. You're gonna be really busy, huh? So Carlos Alvarez asked, really dig the presentation. I didn't know about the LIGO for detecting. Okay, so that was just more of a, that wasn't a question, but he said he really dug the presentation, so that's awesome. Comment Kevliv asked, oh sorry, that's also not a question. That's also, sorry, these aren't questions. I think people just thought that this was really cool, so I guess you did a really great job at explaining it, because black holes are a pretty, oh, that's Comet Kev, that's my friend Kevin. Hi Kevin. Awesome. Well, thank you, Brina.
Thank you.
All right. Our next presenter is Richard Camuccio. Richard got his Bachelor's of Science in Physics from Franklin and Marshall College. Right before this we were practicing and I accidentally said Martian instead of Marshall. I did it again right now.
Just admit it, it's Martian.
Yeah, it should just be Martian. Bachelor's of Science in Physics from Franklin and Marshall College in Pennsylvania. Master's of Science in Physics from UTRGV more recently, and that was this year. And he's currently up in North Texas now getting his PhD in physics at a Texas Tech University. So you've been through a lot of school. And Richard was actually part of the Space City panel that we held in February. So one of the last physical in-person events that STARS got to hold was the Brownsville 2030 panel and networking mixer, and that was at the first annual Crossroads Festival in Brownsville, where we talked about Brownsville's the fact that Brownsville is going to become a space city by 2030, and it's already here. It's already happening. We have SpaceX at Boca Chica building Starship, and we have we're here talking about the different kinds of astrophysics research going on. So I think it's happening a lot sooner than 2030, and so that's really great. And so Richard is going to now present his presentation, which we called an astronomical journey. So, Richard, take it away.
Okay, can you all see this? Can you hear me okay?
Yes, to both.
Okay, great. So I guess I have roughly 15 minutes, and I'm going to spend that time showing you the night sky in a way that we can best do it online. I'd rather be doing this behind the Cristina Torres Memorial Observatory back in Brownsville with everybody standing around. So this is the best we can do given the current situation. So I'm going to give you an astronomical journey of the night sky. And here's more or less what I'm going to talk about. I'm going to talk about time, particularly tonight, as if we just looked up at the night sky tonight. And we're going to go through most of the primary objects that you could see with the naked eye and with binoculars. And we're also going to study the late September sky to understand the different objects that are in it now into October and through October, which these are two of the best planet viewing seasons in the entire year. And I'm going to show you a little bit about sky maps, where you can find some, and also some other events related to meteors that are going to be happening this month with the near-Earth objects, NEOs, and some October meteor showers, which I think I saw someone mention to go see meteor showers in the YouTube chat, and this is good because I'll be talking about the two next major ones, which are both in October. So to understand tonight, or any night that you want to observe, you have to understand a little bit about how the sun sets and how that influences the brightness of the sky. So if you're kind of looking at the horizon, and this is like a slice through the horizon, so you're on the red line and you're just looking out and the sun's setting. So sunset is when the sun reaches the horizon. That's kind of that reference point there. But as the sun sets, it doesn't immediately get dark, and there's better and better times to observe, depending on what you're doing, either casually or scientifically, or if you're looking at a very bright object, it'll appear first in the sky, and then the later night will reveal the fainter objects. So there's three types of twilight that actually exist, and this is just crucial to talk about right now, because I'm going to be using those terms in a little bit. So I wanted to define them, and they're defined as basically how low below the horizon did the sun go. So once it reaches 6 degrees below the horizon, it's ended its civil twilight, and it reaches nautical twilight. And it does that for another 6 degrees until it reaches astronomical twilight. And by a total of 18 degrees below the horizon, you've reached full night. And this is the point at which really detailed astronomical observations can begin. But you don't have to wait this long. This is usually a little over an hour after sunset. So you can start to see objects soon before this happens. So, and so with that, then for tonight, and there's actually a flyer that went out that we put this to, kind of a less detailed version of this. But basically for tonight, if you were to go out, we just ended nautical twilight right now, a minute ago, right? Nautical twilight was at 8:10. Right now it's 8:11. So we just ended nautical twilight, and we've entered astronomical twilight for the next 26 minutes. And by the end of this 26 minutes, pretty much, well, I'll hopefully be done talking by then. I think I will be. That this will be the end of astronomical twilight, and you can begin photometric observations for all of the And on the flip side, then we get reverse order until sunrise. So when it's 18 degrees and rising above the horizon, it's beginning astronomical twilight. And so tomorrow morning at 6 a.m., basically, that's when that starts, until it gets brighter and brighter and sunrise occurs at 7:19 in the morning. So you're looking at basically an observing window for basically, all scientific measurements. You get about 9.5 hours tonight from 8:30 to 6 a.m. And before and after these 2 points, you can also include total observing. So this is like the whole night basically, and it's 2 minutes short of 12 hours. So basically you can observe for quite a while if you were just standing there, if you had the stamina to stand there, or if you had binoculars, you just have a backyard telescope, you could take it outside, and throughout the night there's different objects that'll pop up. And so with that, I am going to show you what those are for this time of the year. I'm going to assume, I think you can see this okay. I have my whole desktop screen shared, so you should be able to see this. Basically,
Yeah, we could see that fine, just so you know.
okay, great, thanks. So I'm going to zoom out, and this is actually in Brownsville digitally, right? So this is like if you're standing outside in your backyard, or if you're at CTMO, at Resaca de la Palma, anywhere. Basically, if you were looking in the south at around 10 o'clock, so you can see where my mouse is down here, this is what the sky would look like at 10 tonight. And the location here is Brownsville, so I have it in the center of Brownsville. Wouldn't be much different up here in Lubbock, but you would see a noticeable shift in all the altitudes of the objects in the sky. So I wanted to be a little bit more accurate for the people in Brownsville and the Valley. But basically, we could start kind of a brief navigation of the sky. I was looking at Andromeda, which I'll get to. And if we start in the west and go to the east to the left, there's quite a variety of objects that you could see that are quite different as well. So you get a really nice difference in category of objects. So everything to the right side here is setting. Everything sets in the west and rises in the east. So over the course of the night, most of these objects are going to proceed to the right if you're looking south. Okay. So starting along the plane of ecliptic, this is where most of the action happens. This is where all the planets orbit, for instance. Starting from the horizon, you get Antares, which is a nice red star. And at that low in the atmosphere, you'll actually see it twinkle even blue. You get very neat color effects because of the star. So if you've seen a particularly weird twinkling red star in the early evening, up to this point, especially if you're up here in Lubbock, where we're actually getting the effects of the California smoke. I'm not sure if you're getting it down there, but that is also causing that to be a lot more prominent. Right before that was Mercury. Mercury is actually visible. It's visible pretty much right after sunset until it sets here at 8:30. So we would have another about 10 to 15 minutes to see it right now, actually. But this is past when it's set. The galaxy is next, and this is Sagittarius, this constellation right here. This is kind of pointing to the center of the galaxy, so there's a lot of neat open clusters and planetary nebula that you could see in here. Proceeding again to the west toward the meridian, which is the highest point in the sky that everything gets to when it goes from left to right, and it passes this green line. That's what I call transiting, and that means it's just at the highest it will go that night, and then it'll start to descend. So Jupiter and Saturn are right next to each other, and you'll see them quite clearly in the sky next to the moon. In between Saturn and Jupiter is Pluto right now, which I could actually show you real quick where that is. So it's right there. So Jupiter is on the right, the brighter one, Saturn's on the left, the dimmer one, and then Pluto. If you had a decently powered telescope with a camera, you would be able to see Pluto. The moon tonight is at 79% and growing. So it's in waxing gibbous phase. It just passed its last quarter, and it's proceeding to full moon next week. And actually at 10 o'clock, it will be basically getting at its highest point. So it's causing a lot of this to be dimmed out. You won't see much of the Milky Way, even with moderate effects of light pollution. Okay, so we keep going to the left just to almost finish this arc. You have this ASP right here, which is the anti-solar point. This is the opposite to where the sun is. So you're kind of looking at the anti-sun. If there was such object orbiting on the other side of the Earth, that's what this is in the sky. And Mars is the last one, and you can see this rising late in the evening, or late in the night, I should say, like toward 10 and 11 p.m. You'll start to see it really get up above the horizon. And I've been observing this week at the student labs here this week at TTU, and you can see with an 8-inch telescope and an eyepiece, like a 25 millimeter or a 14 millimeter eyepiece, you could see the polar caps of Mars right now. So there's definitely not a dust storm occurring, but usually every few months there's a global scale dust storm that blocks out most of the features of Mars. So right now it appears to be in a quiescent phase. And on top of that, in the next month, October is the best month to view Mars, and it will reach perigee, which is the closest approach to Earth, in October. So it's entering into its best time to observe around this time of the year. And also, just for non-naked eye planets, Uranus and Neptune are also in the sky, but you wouldn't be able to see them. If you have really exceptional vision and you're in a dark spot, you could see Uranus at it's at 5.7th magnitude, which is just shy of the limit for human sight. So you could still see that. Now, if you were to go up from there, just a couple of more objects to talk about. There's Andromeda and Triangulum, which are the two nearest galaxies to us. We're currently merging with Andromeda right now. Many of you might have heard that we're going to merge with it, but there was a paper released 2 weeks ago that showed from measurements we are starting to merge with it. There's outer shells of magnetic field mainly, and ionized gas that is on the periphery of both of the galaxies, and they're starting to interact with each other right now. So that's up in the sky. Cassiopeia is above them, and back to the west, you'll have the summer triangle, Deneb, Vega, and Altair, which are going to be basically right above you. And then a couple of the northern constellations. This is to the north, looking down toward the horizon. So it's almost like we're looking backward from where we started. You have Ursa Minor, Ursa Major, Hercules, Cygnus the Swan, Cepheus, and Cassiopeia being the prominent northern constellations right now. You can see a lot of neat clusters in there. So all of these little yellow spots are clusters that you could see with a small telescope, and they're all up in the sky right now. Okay, so I'm going to go back to my presentation real quick. I know I might be going a little fast, I can't really tell, but I want to make sure. I think I'm going to be done at 2025. What I'm using is essentially this is just a digital version, but this is a website up here that produces these every month. So this is for September of 2020. And this is showing basically every major thing I just showed you. And you can kind of see it here. This is like looking south. And you see that line, there's the ecliptic, here's Jupiter, Saturn, Mars is down over here. So this is showing the same thing. It's showing some interesting moments in the sky, like the moon might be near a planet, for instance, and what time that's at. What time that's at. And then on the next page, it'll show you all the neat clusters that I was talking about that you can see in all the constellations where they are. So these are really neat. The digital version I was using is free, and it's for all these different systems. It's Stellarium. It's pretty cool. I'm just showing you how I use this. And the last part I'm going to talk about are just stuff with asteroids, which Wendy talked about already. And if there's any particular questions related to asteroids, I'm going to field them to Wendy, because she's the asteroid hunting expert at CTMO. So, but I'm going to talk about kind of opportunities that are going to happen in October with meteor showers. And then I'm going to end on some final interesting thing with NEOs. So with meteor showers, there's going to be two major events in October, the Draconids and the Orionids. For the Draconids, they emanate from the head of Draco. This is why I was telling you about Draco, and I can show you where that would be in the sky. So if you were to look up to the north, Draco's head is right here. So they'll be shooting out radially from this direction in all different directions. So the best way to look for these is to look away to the middle part of the sky as they streak across. It's not going to help to look right where they come from, right? So they're usually quiet, but they have a history of outburst years. So in 1933 and 1946, for instance, they produced thousands per hour. And just let that number sink into your head. Imagine looking up at the night sky. How many per minute would that require for 1,000 in an hour? That's a lot. In 2011, just back in, just under a decade ago, 600 per hour were logged in some places. This was in Europe. It's produced by this comet, Giacobini-Zinner, with a 6.6-year orbit. It goes out to Jupiter at its farthest extent, and it comes in to as close to the sun as Earth is. And that was back in 2018. So in 2024, 25, it's going to be back, and we might see another peak in these. So I wouldn't expect something to be too exciting, but you never know. The best night is the night of the 7th, but you can start to see them as early as the 6th until the 10th. And for Orionids, Orionids are kind of in a different category. They're produced by Halley's Comet. They're one of the 2 annual meteor showers that are caused by Halley, but this is the October one. There's also one, I think, in April, Eta Aquarids, but I actually don't remember what month they occur in. Earlier in the year, nonetheless. They come from the Club of Orion, which, if I can actually pull up Orion, I think Orion has fully risen yet. But basically, oh wait, what am I doing? I'm looking in the wrong direction. If you look at his upturned hand, they're going to come from that, right? Can't find it. Well, I can't seem to find Orion, but they come from his hand. So you're not going to want to look at the hand. This is basically my point in the previous one, is where they come from. That's the part that you don't want to look for. They're infrequent in the sense that they only produce up to 10 to 20 per hour at peak, but they're fast. They go up to 41 miles per second. And Comet Halley will come back at its closest approach in, I think, 2061. So these peaks usually occur when they get to their closest approach to Earth. So that's for meteor showers in October. The last thing I'm going to talk about is just kind of a happen chance discovery that I was looking at when I was doing this research. And this is a site that Wendy will be very familiar with. It's the Sky Live. She actually introduced it to me. And it tells you all the near-Earth objects that we know about, I should say, because there's many that we don't know about. But the ones that we do know about, we can see when they're going to make their closest approach to Earth. And these are at most somewhat like the order of 2 lunar distances away. So anything within 2 lunar distances, they're considering a near-Earth object. And the yellow and red ones are the closest ones, but this is the one that I found. This was the closest one of the year. It just happened on the 24th at, this would be 6:13 a.m. our time. And look how close it approached the Earth. It was 28,000 kilometers away. That's 4.4 Earth radii away. Now, this is the closest one for the whole year. There's one coming up in December that'll approach 50,000. But the fact is that this thing just whipped right by us on September 24th in the morning. When you click on it, this is where it was. And it's already, so just on the 24th, I looked at this. This was 18th magnitude, which means you would need CTMO's primary telescope to look at it. You could see it. But just in 2 days, it's gone up to 31st magnitude, which you would need then the James Webb telescope to see. So basically what I'm saying is we should be looking for these things. And I'm going to end my talk right there. So this is what's going on late September, early October in our sky. Thank you very much.
Thank you. That's so cool. I'm not going to lie. I was hoping you'd talk more about Orion. That's my favorite one. So
Sorry, I couldn't find it.
it's okay. It comes up pretty late. It'll come up earlier, closer to the winter. So I'm looking forward to that. But before we get into the questions, what inspired you? Why, Maki asks, why astronomy? So yeah, just the overall question of what got you interested, why are you doing this, and why astronomy?
Yeah, sure. So I'm trying to think. I liked astronomy since I could remember, which would be 3 or 4, and I had a telescope when I was 6, so I was looking at the moon quite early, and I was just gathering that these were places rather than things in the sky. So I had this very deep connection at an early age, I think, and my parents and grandparents really brought me to that. And I also had a real fascination my whole life in aviation and flying, and so I've always had these 2 things in my heart, and that's basically made every fundamental decision along my path in my career up to this point. It's just, what does it take to go into space? And I decided, I figured out, you can figure this out too. As somebody asked a question, how do you become an astronaut? There's a particular path that's detailed that you can follow, and it's not going to guarantee you'll become an astronaut, but I'd rather maximize my chances. So that's what I'm doing constantly. Yeah.
That's awesome. So what's your favorite constellation out of all the ones you? Oh, I guess in general, but bonus.
I mean, it's Orion, which is hilarious. Why I couldn't find it too. I was like,
yeah, Orion's cool. I also like it because Taurus is there, and I'm a Taurus, and so I like the combined constellation thing.
yeah, that's true.
So you mentioned Andromeda. I wanted you to talk a little bit more about. I wanted to ask a little bit more about that. And so, Andromeda, I know, is the closest galaxy to us. And I heard. I think just yesterday. I haven't actually even seen it in the sky yet. I've been trying to, but it hasn't been out while I've been stargazing. But I heard that if you can see it, it's actually like the width of it in the sky from our view is about the width of the moon.
Yeah. Yeah, I mean, I don't know if I could reshare. So, just Andromeda, right?
Yeah.
Let me share my screen again real quick. So, yeah. So, with Andromeda, I think over here on the side, you can see it says size 3 degrees on a side, so it's 3 degrees long and 1 degree wide. That's huge. It's our nearest extragalactic neighbor. And yeah, it's, if you look at it comparatively to the moon, it's kind of hard to hear, but you would see that it's of that size. So yeah, it's pretty crazy.
And it's coming towards us, right?
Yeah, we're already starting to touch it, basically. That's what that one paper said a few weeks ago. We've measured the interaction between us, and it's already shown that we're beginning the merger a couple of million years ahead of when we will actually go through each other. Wow. So we're already starting that process on an astronomical timescale right now. That's what's crazy about it. It was a Nature paper too, so it was a big deal.
That is crazy. I started reading a little bit about it, and I started The End of the Universe by Katie Mack, and yeah, I was talking about how I think maybe in 4 billion years that galaxy is going to clash with our galaxy, and it's just going to be one of the most violent events. But we'll probably be calmed down by then. So you mentioned, okay, so can you go back to Stellarium? I wanted to ask you a little bit more about all the data that you see there on the side. So, you mentioned that anybody could download Stellarium and do this themselves and, check out what's in the sky and look at all this data. But can you just briefly go through some of maybe just the highlights, the important data that's on the left side, like the magnitude and the...
Yeah, absolutely. Well, we're looking at Andromeda right now, so this is a great example. At the top, you're just getting different names. So these are just different types of versions of the name for Andromeda. And the highlights, I would say, are what type of object it is. So all these different icons I have are representing different types of objects. And there's more. I mean, I'm not showing half of them. Like if I just click one button, suddenly, wow, boom, those are all the pulsars we've ever discovered. Or there's all the quasars we've ever discovered, right? So there's a lot of objects that you're not seeing. But the type of object up here is going to be really important, even down to these letters. I mean, I'm not going to go into this, but this basically means what type of galaxy it is, down to the morphology. Magnitude, color, surface brightness, contrast index, these are all just brightness values. Magnitude is probably going to be the one most familiar to people. And the fact that this is 3.44, it's below 6, and anything below 6 is visible to the naked eye. So this is going to be a really helpful number for people. All of these numbers here are different ways to express where it is on the sky, nothing more. So I guess the most basic analogy would be X and Y. You have coordinates. This is where it is along these lines, and this is where it is along these lines. And so you can specify where it is on the sky with all of these numbers. And then probably down here, the last thing, I already talked about size, there's distance, and this is how far away it is. So if somebody asks, how far away is Andromeda? This number right here, this is 2.5 million light years away. So you get distance to these objects as well from Stellarium.
Cool. So last question, it's from YouTube. Jen Gabler says, we're staying home 99.5% of the time right now, like we all should, and really struggle to see anything in the night sky from home. Where is a good COVID-safe place to look from nearby? So, I hope you remember Brownsville.
Yeah, I guess it depends on where you are in Brownsville. I'm trying to think. I've lived in the North Alton Glore area, and then I lived pretty much close to the border by the university campus in Brownsville. So definitely, the farther south you go, it's going to be rough with the light pollution. I would say Maki wrote the Cristina Torres Memorial Observatory, so I know you can go there. At least that park's not closed when I was still in Brownsville a couple of months ago. So you can always go there and take a walk. And towards sunset, yeah, the trees are really high, so you might not be able to see some of the objects low on the horizon, but all of those galaxies and clusters are up there. Also, Wendy just said Laguna, so Laguna Atascosa, which we've done stargazing events there before. That one's great because it's even farther away from the light effects of Brownsville. Brina gave a good one, is the island as well, so you can go up to the island. I've seen some of the highest contrasting Milky Way I've ever seen in my life in the north part of the island at like 4 a.m. So that area is also good for looking at things for safe social distancing. In your backyard, though, if you get even a decent pair of binoculars, you could see the fuzzy patch of Andromeda. You could probably see some of the bigger nebula, like the Omega Cluster and Orion's Nebula, and all the planets too. So, like, even just standing in your backyard with a pair of binoculars is really going to do a number of differences.
Yeah. Okay, cool. So yeah, I'll end it there, but I wanted to just make a quick comment about, I know before you started talking, you said that you know, ideally we would be doing this in person, right, at the Cristina Torres Memorial Observatory or Laguna Tascosa National Wildlife Refuge, where we have had star parties before. So earlier, I just wanted to mention that earlier this year, you were a big player in putting together an itinerary for recurring stargazing parties that were supposed to happen at Resaca de la Palma State Park. Unfortunately, with the COVID situation, we were not able to go through with that. So, but for now, I mean, I just want to say thank you. I know you moved to Texas Tech to get your PhD, and so we thought that, you know, we were the first star party we were able to do. You weren't going to be involved in that, and here you are. Technically, this is the first star party, and you were involved in it, and so that's awesome. And to our viewers and to the, you know, followers of stars, we are hoping we're going to continue to do stuff like this online to provide that stargazing for you guys until we can go back to the observatory and go back to the parks and do this in person.
Yeah, so thank you for the opportunity to talk. And I'm actually looking at the YouTube live stream right now, so I'm helping answer questions as best I can. So keep them coming, people. Keep them coming.
Yeah, okay, well, I think that's all the time we had, right? Yeah. All right, cool. So thank you, Richard. Okay. So next we're going to close this out with a walkthrough of the Cristina Torres Memorial Observatory. But before that, we're actually going to have the STAR's initial founder, Carol Lutzinger, talk a little bit about today, about International Astronomy Day and International Observe the Moon Night, which, if you weren't here for the first part of the live stream, it just so happened that and landed on today, on September 26th, 2020. It doesn't usually happen, but it did this year. And so Carol's going to talk a little bit about those holidays and why they matter, and, you know, why we're here talking about them today.
Hi, Victor, and everybody else. We're so glad you joined us tonight. And this is a magical time for me, as you can imagine, getting to be on a Zoom and a YouTube and talk about astronomy and space. And this Observe the Moon Night, you haven't been out yet to look at it, I'm sure, but when the program is over, I hope you do go outside and look up. The International and National Observe the Moon Night is just something that people cooked up because they really like looking at the moon. And several years ago, NASA sent an orbiting spacecraft called LRO, Lunar Reconnaissance Orbiter. It's been orbiting the moon now for quite a long time, and it's just kind of to celebrate going out and looking up. And the sky was clear the last time I checked, and I hope that you take a walk outside and go look up. And thank you so much for joining us this evening.
Thank you very much. Okay.
My pleasure.
So now, in celebration of International Observe the Moon Night. By the way, I wanted to mention that this image behind me is not one of the Zoom default images. This is actually an image taken by Richard on July 1st of this year at the Cristina Torres Memorial Observatory. And so we're able to do a lot of cool stuff there. And Alex Reyes is going to be our next presenter now, and he's going to give us a little walkthrough about that. Alex is getting right now his Bachelor's of Science. He received his Bachelor's of Science in Physics from UTRGV recently, and he's currently now getting his Master's in Physics at UTRGV. Alex, do you want to take it away?
Hi, can you hear me?
Yes.
Awesome. Okay. So hi, my name is Alejandro Reyes, and I'm standing here at Resaca de la Palma State Park. Behind me is the visitor center to Resaca de la Palma, and in front of me, right behind you, is CTMO, the Cristina Torres Memorial Observatory. It was formerly known as Nombre Bueno. Nombre Bueno means beyond the sky in the Mapuche language of people indigenous to Argentina, but it has been renamed Cristina Torres Memorial Observatory in memory of a former professor, Cristina Torres, from UTD. Cristina Torres was a professor who worked here at UTV. Her work helped LIGO in the detection of the first gravitational wave confirmation. She passed away in March of 2015. And if you follow me, we'll go into the dome, and I'll talk a little bit about what we do here and the process that goes down in South Texas. Now you might be wondering, what does the schedule of a local astronomer look like? Well, the first thing that we do is we have to look at the local weather in the morning. We have to see and check the cloud coverage and the chances of rain. These two are the main factors that are going to dictate how our night's going to go. Any cloud coverage below 50% means we might be good to go. And if you see tonight, it's a very clear night. We'll take some pictures of the moon tonight, and hopefully we'll be able to show this to you live. What you see here to my left is a farm of 9 mini domes. I'll show you a picture in the daylight, so it doesn't look like a Blair Witch Project scene. But these domes are going to house telescopes that are going to be controlled remotely. And we are in the process of installing those telescopes. We're going to be training local instructors and science teachers so they can use these telescopes from the classroom and help them teach. Now, if you come with me, I'm really excited because we're going to have visitors for the first time since the pandemic started. Come on in. The first thing that you'll notice here, and this is Martinez Valencia. Hello. He's working on his bachelor's in physics at UTRGV. First thing you'll notice is this frame right here. This is under construction, and this will be a room that's gonna protect us, shelter us from the elements. Can you come with me? The first step when entering the dome is texting or messaging the rest of the group that the dome has been opened. This is for security purposes. Now, on the top here, on one of the walls of the dome, you see there a motor, a controller with a battery. That battery has to be charged every night, and that controller is connected to that motor at the top. And Marcelo, you kindly finish opening up the shutter window. Sure. It is now remote controlled. And you come this way. Here we have a telescope. 17-inch plane-wave telescope. It is a Cassian reflector telescope. That means in this part right here, there are 2 mirrors. A primary mirror on the back of the telescope, and there's a secondary mirror about here. Now, the light is coming in from the front of the telescope. It reflects from the first primary mirror onto the secondary mirror, and then it comes back out through a hole in the back. Now, the second part of the telescope is the camera. If you come this way, you see the camera right there. One of the first steps is what is pulling down the camera. This is in order to mitigate a lot of the noise that comes from the electronics. And that camera, it works the same way as your cell phone camera. It's a CCD and charge coupled device. But of course, it's a lot more sensitive, and we'll show you some pictures towards the end. The third part of the telescope is this, the mount, which is automatically controlled from Atlas, which is our computer back here. And this mount is attached to the pier and the pedestal. It's bolted down to the ground. We need this, the whole system, to be very still. And actually, we have some signs here that this is not a table. In the past, while taking pictures, long exposures, placing things here, or even moving or leaning against the pedestal, can make our pictures come up blurry. So this is how sensitive our instrument is. Back here, we have lights. We have power switch controllers and a switch box in the back. Now, we would like to show you a picture of the moon tonight. So the first step is we're going to slew the telescope going at the moon. If you come this way, you see the moon is right there. We have rotated the dome so that the moon is visible through the window. And Martinez would like to switch to slew the telescope. Awesome. And we can watch through the other side, so we can see the image coming out of Atlas, our computer, taking the exposure. So we follow. All right. So for these moon images, do you want to? Sure. So here we have this software, which helps us say the configuration for the frames. So how long the exposure is going to be, the type of filters that we use, and I'll talk about the filters in a moment. But here we're going to use an exposure of 400ths of a second. and the filter is going to be in Johnson B. Ooh. Okay, now, nice shot. Now, this picture looks very oversaturated on this side. We'll need to clean it up. And in the presentation, I'm going to show you how it would look like once we do that. So let me switch over to my presentation.
And the reason why we would need to clean up this image of the moon is because the moon is such a bright object, and our telescope is so sensitive to faint objects that you have to process this image in order to actually get the full details of the image. And that's we don't want to make you go through the process of boring stuff of processing and stuff like that. So
running the algorithms.
Running the algorithms, exactly.
So this is the promised picture in broad daylight of CTMO, Cristina Torres Memorial Observatory. It's a picture close to twilight of the dome, already open. And here we have a picture, I really like this picture. It's a long exposure of one of our public events. Here in the background, you can see some star trails. And one other important factor that we have to look into when selecting an object to observe and planning out the night is when the object rises from the east and when it sets from the west. And the window to observe that object is going to be when it's closest to our zenith, or the point right above us. Here you can see a better picture of the telescope. This is the telescope here. The secondary mirror would be located here inside of the casing. And this is the automatic mount. And here I'd like to show you some pictures we've taken. These are from over a year ago. This is a search for supernova events. And on the left, you can see the reference frame from a catalog. And this is a picture taken at CTMO with a previous telescope. And on the left, the catalog. At the bottom, you can see what we call a catalog or sources. We run a pipeline, a code, which cleans up the images that we take, and it also extracts the position and the names of the sources or the objects in the sky that we can see within each frame. Here we see what a galaxy should look like. This is NGC 7345. This is the picture from here, from our telescope. It's a cluster of galaxies. We can see a number of galaxies here, and this is how it looks like from our telescope. And I've included some here to explain a little bit about blurry images. Since we're looking for supernova events, even these pictures where you can barely see some of the galaxies, a supernova explosion is so powerful that it overpowers the brightness of its host galaxy. So if a supernova happened here, we'll be able to see it once we go back and take another exposure and compare the two. Another image taken also here at CPMO. Now we're also leading efforts in creating false color images from our exposures here at CTMO. On the left here is a frame taken on August 6th of the M16 nebula, the Eagle Nebula. And I'm sure you've seen this before. I'll show you a picture of it by Hubble telescope. But the way that we do this is that we take frames in 3 different filters. And the very same way that every color can be created from the 3 primary colors, red, green, and blue, analogous to that, we take 3 different filters or 3 different colors, and then we combine those 3 pictures to get a colored images. On the right, this is the same image with its contrast set to really high. And here you can see a comparison. This is what the Eagle Nebula looks like. This is a photograph by the Hubble telescope. And this is our image here at CPMO. And this was taken with this telescope, with the new upgraded telescope. If you would like to see it closer, here is the pillars of creation. And this is what it looks like from here. We are still working on cleaning up the data. You can see some artifacts here. These stars look like rainbows, and they should look like white dots. So we're working on improving that. And here's a aerial picture from CTMO and the 9 mini-domes that we were talking about. And here we can see a photograph taken by Victor Camuccio back in July 1st of the moon. After processing in 20 minutes. And that's our presentation. Any questions?
Yeah, can we have the image you take of the moon? And I think it would be really cool for International Observe the Moon Night to, after you process it, if you have to, we'll post that later for everybody that was watching the live stream so that they could see them. They could see those.
Sure. We'll send that over to you.
How long does it take to process those images?
It shouldn't take too long. We have the pipeline here installed on Atlas, so maybe within the next 20-30 minutes, we'll have that ready for you.
Okay, cool. So we are running a little bit short on time. Before we go, I want to ask all of you, Alex, Martel, and Emmanuel, why are you guys so interested in astronomy? What led you guys, to be at an observatory right now?
Well, for me, it's exciting to know that every night I can take an exposure, I can take a frame that could have something that's new to human knowledge. It can confirm the existence of something we haven't discovered yet, and that is really exciting. Coming every time is like playing the lottery, and and finding something new would be the prize, basically.
Cool.
Yeah, and my answer is kind of similar to Alex's, where it's very exciting to be able to be part of research that can discover new things about physics and astronomy, and that's always very exciting because you want to be that type of person that discovers something, or that is actively part of the scientific community. And it's also just very awesome and exciting to be able to take these images and see the universe for yourself with your own eyes, with all these instruments and stuff. Of course, you can do this with your own telescopes, but just to have this sort of equipment on hand makes the experience so much better. And that is why I like coming out here in the middle of nowhere.
Cool. So Emmanuel, I know you're the cameraman, but I'm gonna put you on the spot and ask you the same question. You're one of I know you came to the group recently, but I was with you at the observatory not too long ago, and I want to know what you like about it and what made you go out there and why you're interested in this too.
Like, the reason I just look at stars in general and just how like the sun and the moon is just teeny. Like, you can walk outside and see how beautiful the stars are. Different constellations they are. But when I come here, I get to look at it on a grander scale. I feel like, oh, look how bright this star is, and look how it actually blooms in the light that I see. Or I can look at the moon, look at the different craters, and I always see I see like a sense of being. Like, I'm supposed to be here. Like, not even my telescope, but through my mind. And it shows me the moon, and it's. You see, let's say Vega, or let's see the net, you say, whoa, it's a beautiful. You look at the different galaxies, and you're like, whoa, there's a bunch of galaxies. And it's a sense of scale, like, they're big, and it makes you seem bigger and and it gives you a place to be here.
Awesome. Well, thank you guys. Like I think we were posting on one of the live stream chats earlier, and we were saying that if I know right now it's hard times and we're not able to host stargazing events at the observatory, but if anybody watching this live stream is interested, we do offer visitations. That it's very limited right now, and we can't have too many people inside the observatory at once. But if anybody is interested, if you want to stargaze with us, just let us know. Let stars know on our social media. Just contact us or through our social media or website, and we can set something up. So thank you guys.
Thank you. One last thing, after the pandemic is over, we plan to have weekly days where the community can come in. It's going to be open to the public.
Thank you.
So
Yeah, that's going to be great. All right. Have a good night, guys.
Good night.
Okay. Stop sharing this. All right.
Well, this about concludes our event for the night, and we would like to thank everybody that helped put this together, and also, of course, thank Dr. Diaz and all our partners. If you like what you saw, please don't hesitate to donate. We just click the donation button in this event to support us and events like this in the future. And we would also like to say that we have a lot of things in the pipeline, and that hopefully with COVID, being under control, we can actually do something responsible and socially distanced, both at the CTMO and at the, of course, Southmost Observatory, which also has their own telescope. So just stay tuned on the social media at Star Society RGV. We are on Instagram, we're on Twitter, we're on Facebook, and of course our website and email we're always available for you guys.
Yeah. This is Maki, by the way. Do you want to introduce yourself?
Everybody knows me. So my name is Maria. Everybody calls me Maki, and I'm actually the media and communications outreach director for STARS. And please don't hesitate to contact us at any time. We are here to serve the community.
Yeah, but thank you to all the presenters. Thank you, Dr. Diaz. Thank you, Brina, Wendy, Richard, Carol, Alex, and Emmanuel Martel for helping Alex. Thank all of you. I also want to give just a quick thank you to our partners. It hasn't been an easy last few months for any of us, but we had a few partners out there helping us push forward and do events. So I want to say thank you to the Children's Museum of Brownsville, Felipe and Amy. You guys, we did some cool stuff there. Laguna Tascosa National Wildlife Refuge, Brownsville Public Library System, and BISD. All of you helped us, keep pushing forward during these times, and now we're here doing online events, and we can't wait to
Do more.
Yeah, we're gonna do a lot of fun stuff online, but we also can't wait until we can all meet up around the telescope and do what we were doing before. So until then, happy International Astronomy Day, happy International Observe the Moon Night, and we'll see you soon.
Be safe.